Hi class, this is Mr. Morris and we're doing a set of notes on types of chemical bonds. This is unit 2.1 in AP Chemistry. Some of this will be review, but some of it absolutely will be new. Start off, when the valence electrons of neighboring atoms are either transferred, shared, or pooled, chemical bonds are formed. I'm going to mostly have the things you need to write in red. So on your notes, make sure that you are keeping up with the things that are in red. And if you need to stop this video to write something down, feel free to do so. So when we have a metal and a nonmetal, that's an ionic bond, which means that the electrons are transferred from one to the other. I want you to also make sure that you take note that even though we say that it's normally a metal and a nonmetal, it could also be a polyatomic ion. It's possible that you would have a polyatomic ion like NH4 reacting with a nonmetal, or with another polyatomic ion, or you'd have a metal like sodium interacting with a polyatomic ion like nitrate. So most of the time we say it is a metal and a nonmetal, but don't forget about polyatomic ions. All right, if we have a nonmetal reacting with a nonmetal, that's going to be a covalent compound, and electrons are shared in this case. If you've got a metal and a metal bonded, that's a metallic bond. It's just metals and metals. And we say the electrons are pooled, or we say it's a sea of electrons. To get more specific, an ionic bond is the attraction between cations and anions after the electrons are transferred from the metal to the nonmetal. Now let's look at an animation of this. As you can see in this animation, we start off with sodium being a neutral atom, and then it gives away an electron. As it gives the electron away, it's turning into a positive ion. Chlorine starts out as a neutral atom, and as it gains that electron that was given to it by sodium, it becomes a negative ion. When that change happens, we've got a positive ion and a negative ion, and they are attracted to each other because of opposite charges. That's Coulombic attraction. A covalent bond is a little different. It's the attraction between the nucleus of atom 1 and the valence electrons of atom 2, and the attraction between the valence electrons of atom 1 and the nucleus of atom 2. The valence electrons attracted to both nuclei are shared electrons. Now let's break that down a little bit more and look at this animation. So you can see that both of these have an unfilled valence shell. So it's an incomplete valence shell. So we have the nucleus of this atom, let's call that atom 1, is attracted to the electrons in the other atom, in atom 2. That allows them to get closer. Now this is atom 2. The nucleus in atom 2 is attracted to the electrons in atom 1. And as they get close to each other, they end up sharing those unpaired electrons between them, and most of the time those electrons spend most of the time between the two atoms. Now let's talk about metallic bonds. That's the attraction between metal cations and delocalized electrons. Delocalized means it's not local anymore. It's not on the same atom that it first came from, but it is very loosely held because, remember, metals have low electronegativity, they have low ionization energy, and they have low electron affinity, so they don't hold onto their electrons very tightly. The valence electrons of the metal atoms are loosely held, so they are delocalized when they're put in a network of a lot of metal atoms. And they are mobile, which means they can move around freely, just like a mobile home or a mobile phone means that it can move. That's what this means. It can move around freely among the metal cations, and this model is called the electron sea model, or the sea of electrons. And you can see image of this. We've got our metal cations, that's those gray circles. It's just the nucleus with the core electrons, so it's a metal cation, and then we've got these loosely held valence electrons that are just buzzing all over the place, and they're not really attached to any single metal atom, but they float throughout a large network of metal cations. Now let's look at this table and break it down a little bit. At the top, you can see your headings: ionic bonds, covalent bonds, and metallic bonds. We're going to break this down as kind of a summary of all of it. The name of the substance that contains an ionic bond is an ionic compound. So if it's got an ionic bond, you know it's an ionic compound. If it's got a covalent bond, there are two names that mean the same thing, and then there's another one that's a little different. So we've got covalent compounds and molecular compounds. Those are just synonyms. They both are compounds with a covalent bond. But don't forget about your diatomic elements. That's like H2, O2, Cl2, N2, and so on. Diatomic elements are also made up of covalent bonds. Then we have metallic bonds. The substance that is made up of metallic bonds, if it's a pure substance, that would be a metal. It's just an element. It's a metal. But if we have a mixture, it's an alloy. Now, alloys are unique substances. We're going to be talking about them in more detail later. The name of a unit in the substance, the unit is another word for the particle. So in an ionic compound, the unit is the formula unit. Now let's look at this diagram up here. You see the huge network solid, a repeating pattern. But if we just took the smallest ratio of chlorine to sodium in this example, it would be 1 purple and 1 green, 1 sodium and 1 chlorine. It's a 1-to-1 ratio. So that's a formula unit, would be 1 of each. A molecule is the smallest unit or particle of a covalent bond. And if you look at this diagram, see there's actually some space between the atoms except in the molecule. You can see these individual H2O molecules, and then between them there's a little bit of space. There's some attraction between them, but it's not the same thing as the chemical bond. Those are called intermolecular forces. We'll get into it. And then we've got our atoms for a metal. For metallic bonding, it's just an atom is the smallest particle or unit. Now, the attractive force between two or more units in an ionic bond is just called an ionic bond. Let me back up. Let's look first at the attractive force within the unit, and pay attention to that word there, within. We're talking about the bond that holds the smallest particle together. It's an ionic bond in ionic compounds. Within a covalent compound, it's the covalent bond. We're talking about that bond between hydrogen and oxygen in this case. And the metallic bond is what holds the metals together in metallic bonding. But then we talk about the attractive force between two or more units. So if I were to just highlight 2 units, or 1 unit, so that's the purple one here and the green one there, just sodium and chlorine. Let's say that I wanted to pull 1 unit off of this network, off of that crystal. If I want to just pull one of those off, you see it would be the same thing as if I were to try to just pull chlorine or sodium off, because they're attracted to each other just as much as they're attracted to these other ions. Okay, they're held together by ionic bonds. The whole thing is. It's a little different when we're talking about a covalent compound because they're held together by intermolecular forces. These intermolecular forces are the attractions between the water molecules, and they're not as strong as the bond inside the water molecule. The attraction between the intermolecular force is not as strong as the bond within the molecule. Metallic bonds, again, kind of like ionic bonds, if I were to pull off one atom, it takes the same amount of energy as if I were to try to separate 2 or 3 of them from the metal. We'll spend some more time on that. Then we've got our properties due to the type of bond and structure. You've got a high melting point for ionic bonds, a high boiling point for ionic bonds. They're hard, they're brittle. For covalent bonds, we have a low melting point, a low boiling point, and they can be soft. They're not always, but they can be soft. With metallic bond, we have a high melting point again, high boiling point. They're hard. They're also malleable and ductile. We get into a little more detail on why these last 2 properties exist in a later set of notes. But all of these properties can be explained to some extent. Oh, by the way, we will be talking more about intermolecular forces in Unit 3. We're in Unit 2 right now, so we're going to be focusing in Unit 2 on the attractive forces within the unit. That's the bond, the ionic, covalent, or metallic bond. But back to our explanations down here, the reason for these properties actually comes from the type of bond that we have, from the type of bond that is between 2 or more units. So having to break an ionic bond in order to melt an ionic compound explains why we have such a high melting point and a high boiling point, because we have to break ionic bonds to make that happen. All right? And with covalent compounds, the reason it's a little bit lower melting point is because we don't have to break a chemical bond like an ionic or covalent or metallic bond. We only have to break intermolecular forces, and they're much weaker. And then we get to metallic bonds. Again, because this is a chemical bond that has to be broken, that leads to the high melting point, high boiling point, some of the other properties. All right, here's another picture that just kind of compares the different bond types. Again, if I were to try to separate one unit of a metal, if I were to try to separate this from the rest of the metal, I would have to break the chemical bond, the metallic bond, in order to do that. If I were to try to separate out one sodium chloride unit from the rest of this crystal lattice, I would have to break some ionic bonds in order to make that happen. But if I'm trying to separate one water molecule from the rest, I just have to break intermolecular forces. So that's why it's so much easier to do that with a covalent compound than with anything else. And we'll spend more time on that in the remainder of these notes. I'm going to go ahead and pause the video right here, and we'll take a little bit of a break before you start the next one.